hopefully this is the last take. So yeah, as the title suggests, this video will provide a quick overview of running a basic implementation of AP-LASR. So I'll start by first giving you an overview of the various steps in this workflow, and then I'll show you various places to find resources and if you run into issues or if you need to debug AP-LASR. And then I'll finally walk through examples. First, using the module system in MSU's HPCC, and then I'll also walk through an example of creating a Conda environment if you happen to be using it in another computing environment, for example, your local computer. So yeah, due to time constraints and the nature of this video, I really won't go through the nitty-gritty details of the theory and background behind ancestral reconstruction. I did provide a link in the description about this. But a couple of points about this that are helpful in terms of understanding and using AP-LASR is that, for one, it's a more technical note, is that AP-LASR through IQ-Tree uses a Bayesian approach to infer ancestral sequences. And AP-LASR, given its title, which is Automated Protein Library Creation, goes beyond ASR in creating these libraries of proteins based on these ancestors, based on the relative uncertainty at each position. And that gives us a powerful tool to efficiently navigate this vast protein design space. At its core, AP-LASR is essentially a Python script that automates a lot of these steps. So working away chronologically, AP-LASR first sources a bunch of related sequences using NCBI/P based on a given protein sequence. And then these sequences together are clustered and trimmed using CD-HIT. And then we're going to, at this step, the main parameters there are to ensure the diversity, and also as a main step for formatting the sequences for alignment. Once these desired sequences have the desired diversity, then we can align these sequences using MAFT. And then after that, IQ-Tree is then used to create construct the phylogenetic tree. And then using that tree, you can construct the most probable ancestor for various nodes in that tree. And then uncertainties that those nodes can be used to create these libraries. And I can show different files along the stage, and these are created as outputs, can enlighten you in terms of kind of demystifying this kind of complex workflow. One thing that I mentioned about the posterior probabilities, and so this is actually another parameter that you can optimize based on like your main biological questions. For example, if you had different assays that you wanted to use, you would want to kind of tailor the number of tailor the library size based on what you're trying to accomplish. And one thing I mentioned, or one thing I didn't mention, is the supplementation. For the purpose of this video, we're going to skip that. But it's a feature that you can use if you have noticeable gaps in alignment, and that could be a topic for another video. So now that's the end of the scripted portion. I'm going to remove this iPad here. And then I'm just going to walk through a couple different resources, both on the shared drive and also on HPCC. And then walk through an example. So everything I'm walking through today is going to be following this path from the shared drive. Is in this folder. So AutoASR tutorials in this Word document is the main document I'm going to be working off in terms of following along, if you would like to follow along with me. So like the AlphaFold documents I created in the past, a quick disclaimer about stuff, basic usage, and then the various options and flags that you can use to customize ASR, and then also helpful examples. And this is all essentially a copy of the GitHub that's publicly available, and then with some customization based on the use on MSU's HPCC. And then also, if you run into issues, there's also a couple of general guidelines in terms of using HPCC, or in terms of using AP-LASR rather. So yeah, getting started. So in its most basic usage, you really only need a sequence. Timestamp here. I totally forgot to mention, in addition to having the sequence that you want to analyze, you would also want to have the script, and I did not describe where to get that. So ideally, you should just download this from the GitHub. This is usually tested enough before being published. So just going ahead and opening up that and downloading that file. That is one way. And if there are also other ways of getting that on the Waldring Lab share, in the AutoASR folder. Why did I press that button? AutoASR folder. And the script would also be in this folder as well. So download that into your working directory, and then you can run AP-LASR from wherever you put that file in the working directory. All right, so now I'm going to return to the previously recorded video. The default mode is ASR, but I'm just going to follow this more typical example where you would submit this as a bash script. So for the purpose of the video, I created an interactive desktop just so we can walk along the different steps, and it helps if you need to troubleshoot along the way for any reason. So I've created these interactive desktops, and basically the same parameters here. So if you press interactive desktop from the top menu here, from on demand. Okay, so I'm going to cut back here. That took a couple minutes and a couple resetting here. So number of hours 12, just for the purposes of this video. And just like this script here, I requested 3 cores per task, and I only have 1 task. And I requested 25 gigabytes of memory per core. It doesn't really matter the node in this context here. So I won't hit launch because I already have a couple available, and they're actually running here. So 2 examples. So one here using a typical module system, and I'll put timestamps here to skip around. So following along, module purge. I will definitely not type this line out. And then so module purge, remove all the modules that are available. Sometimes they don't play well with each other. And then we'll load the various programs. GCC is like a compiler and different tools associated with that. OpenMPI is for multitasking tasks, especially for IQ tree. BioPython is for various bioinformatics related tasks here. Math for, as I mentioned before, is alignment. CD hit is for clustering and formatting these sequences. IQ tree, as mentioned before, also is for the constructing the phylogenetic tree and also inferring the ancestors. And the matplotlib for graphing and making figures. So that's that. That's what's happening with that command. So as I mentioned before, everything is on this folder here. This is actually output. I'll put the input folder somewhere around here. And so if I, if I get there, all you need, as I mentioned before, all you need is a sequence. And as you can see from here, you can even just type in a sequence if you prefer, and that's generally not recommended. But usually we define that in the fastest sequence, and you can have multiple sequences input as well. But for the purpose of the video, for this basic implementation, this folder or file, I wonder if I can get this relatively quickly. If not, I will not deal with this. All right, it seems to be very slow today, so I won't do that. But it's just one sequence, and you can have multiple sequences if you wish. And there's also a feature to include outgroups, which will not be covered in this video as well. But if you want to define an outgroup, that is also an option as well. So now we have everything loaded, and we can just call AP-LASR here. There's a very minor difference detail here with v3, but just refer everything to AP-LASR. So it's running, and I actually ran this earlier before, so I'm going to go ahead and cancel that. And so that's pretty much it. It'll run maybe, depending on the complexity of sequence and how many sequences you have, up to a couple hours. This example is actually not particularly demanding. I think it only took an hour or 2 earlier today. But we can walk through some examples, and I've also downloaded these examples here in this tutorial folder. I'll rename it probably to make it more easy to reference. It'll probably be like output folder, but it's a little easier to navigate here on Microsoft Visual Studio Code. So that's the same folder here. So where to start on these results? So yeah, with the libraries. So these are very essentially FASTA files with the different DNA libraries. I believe they are codon optimized for a human mammalian expression. I can double check the notes on that, but that's there. And there's it. AP-LASR automatically runs it for various thresholds, and you can get a sense of these thresholds. So essentially, the lower the threshold, the less stringent it is about the probability of having that. So you'll see here with a 0.25%, I think that's 0.25% here. You'll have less, and as you decrease the threshold, you'll have increasingly large number of different sequences, essentially. So that's that in the DNA libraries folder. ASR folder has a couple other interesting stuff here. So the confidence.txt will tell you the number of nodes and the average confidence of those nodes. And it'll also give you some additional details there. The state file is also particularly interesting. So for every single position and every single, or so it'll essentially give you the probabilities to have every single, or every amino acid at every single position for every single ancestor. This isn't quite the easiest way to navigate this. You can also open this in Excel, and I think I might play around with making an interactive widget eventually one day. But that's important in terms of understanding the state file, because in terms of constructing the libraries, this is what we used in terms of, so if we define a cutoff of 0.25%, we want a minimum 0.25% for a given amino acid, and then we'll add that to the library. So that's a little context behind that, and you can visualize this with the confidence.png. Oh, there we go, if it loads. Okay. And then other results that are worth mentioning. So the hits info will give you information about, so after submitting the initial sequence to NCBI's BLAST-P search, so this is our results from that search. And then it will tell us, then we'll have also alignments with the gaps and without the gaps. And then we'll also have a tree file, the string, and I typically use Figtree. There are a bunch of other visualization tools, and there's also a couple tools that we haven't quite documented yet on creating more human readable text. So these are the session numbers, but you can convert this into various like species information. So this is a Figtree. So with that being said, so that's pretty much it for the video. For now, I'm gonna skip on to an example. If you, for example, wanted to run AP-LASR on a computing environment that did not have this module system, so essentially creating a Conda environment, if for some reason the modules don't work. And sometimes that has happened in the past, modules kind of break sometimes. Usually ISO support is pretty helpful in terms of resolving those issues, but if for some reason they don't work, I've also outlined a way to create a Conda environment so you can to get around those issues. And it's all based around creating an environment based on this YAML file. And that file essentially tells Conda all the programs that you need to run AP-LASR and the places to find those programs to install. And I just name it default AP-LASR. And we're just going to walk through those steps right here. So however you installed Conda in whatever environment you're working out of, make sure it's running. For this example on MSU's HPCC, there's a couple steps here. So like before, we need to purge the modules, then go ahead and load Conda. And then from that, I have this loaded on one of my working directories here. All right, here, yeah, so my YAML file is in this working directory here. Then to create the environment, just call Conda environment create from a file with that F, and that file is ap-lasr.yaml. And then I will probably speed this up till when it's done. It may take a second. Okay. As you can see from the clock on the upright, that took just a couple minutes there, and I'll probably speed it up to be about like 30x to make sure that only took like 5 seconds or so. So I'm going to go ahead and activate the environment. And I already have an environment named AP-LASR for testing before, so I just renamed that demonstration. And then just like before, I can just call AP-LASR, but essentially it'll give you the same results, but if for some reason modules don't work. One thing I didn't mention was when that was all installing, there were a couple modes. So I just ran through a basic example. So there are a couple modes here. If you wanted to remake the libraries based on a user's threshold, and the option for that is T here as a decimal. Another operating mode is the assist mode. It will essentially give you a printout of this within the command line, and that's useful if you don't want to dig around different documents here. And then there's also the make the figures. But that should be a quick overview of AP-LASR.